Alexey, please.
Okay, thanks, Ivan, for kind introduction. Good morning, everyone. Indeed, the topic is hot, but I'll speak actually about very simple things. Maybe because I am getting older, and I'll take a bit pedagogical note. So those who still don't know what is dynamical meaningful theory, I will try to explain it. Very simple words. Well, and the plots I'm going to show you are obtained in collaboration with Sal Semyonov, who is my PhD student in Moscow, and Sasha Lichtenstein of Hamburg University. Good. I will start from very old time, from the time of Mott. Then he came with this famous idea of Mott insulator. So just to remind you, if you start from base theory, then there are very strict rules which compounds can be insulating and which cannot be. Just simply, if you have an odd number of electrons per unit cell, then the compound must be metallic. But this is not always true. For many transition metal oxides, this is not true. In particular, for this nickel oxygen. There is a graph, and Vadim Brashkin would love to see an exponent here. So this is definitely an insulator. So how would it be? The crystal structure of this oxide is extremely simple. It's like natrium chloride or whatever. So what Sir Neville Francis Mott proposed, he proposed to see this, call this reaction. Then an electron goes from one nickel atom to another one. So you have here what's written on the bottom line. Why this can happen? Because of the Coulomb interaction. Because it's energetically more favorable to have the right-hand side of this equation than to have the left-hand side of this equation, because of what is nowadays called Hubbard U. But there is a problem. You should somehow pick which nickel atoms gain electrons and which lose electrons. So there should be some superlattice, say, some period doubling to organize this in an ordered manner. But experimentally, there is no period doubling. There is no any signatures of the ordering. So what Mott proposed to say, he told it in words, that this must happen dynamically. So what would we say now? This happens because of some fluctuations. So please remember, Mott means fluctuations. So the next important step is, of course, Hubbard with his famous Hubbard model. Let me remind that nowadays Hubbard model is attributed to a planar system. But at the time of Hubbard, he was talking, of course, about the bulk system, about the 3D system. But the rest is what we are accustomed to. So electrons travel on a simple lattice. They hop to the nearest neighbors, and they dislike each other because of the Hubbard attraction term Hubbard repulsion term, sorry, U. And basically, back to this this explanation of the mode the electricity, mode insulation. So Hubbard told that there must be some critical value of the Coulomb local repulsion, above which electrons do not travel over the lattice. They are localized at particular sites because there are other electrons at neighboring sites. And, this makes the localized wave functions more energetically favorable than the Bloch waves. So this is what we call local correlations. So you see, there is no idea of fluctuations here. On this language, you can call it Coulomb blockade, whatever, but this is local physics. This is not what initially was proposed by Watt. So Hubbard means locality, and actually these two concepts, they somehow coexist and compete till nowadays. Well, I'm going to present some numerical data obtained within our approach and compare them to numerically exact data on this simple Drosophila system. This is a Hubbard lattice 8 by 8 sites periodized. So why do I plot these sites? Because I want you to see that this system is not very small. It's a medium-sized system, 64 sites. But it is small enough to think that in terms of the order parameter, this system tends to the antiferromagnetism. In terms of the order parameter, this is more Landau-like, not Landau-Ginzburg-like system. You don't have large, at least, space fluctuations. I will consider this situation as Drosophila in the sense that there is just a single collective antiferromagnetic mode, and I will stay not far from half filling, so that there is no superconductivity, there is no charge density waves, no spin waves, nothing, just antiferromagnetism. Good. On the other hand, I will take U equal 5T. So this is pretty the strongly correlated system. So that's it. In certain sense, it's simple. In other sense, it's not as simple. Sometimes the simplified systems are more difficult than the big ones. Okay. Now about the contemporary view to the local correlations problem. So this is what was understood in basically in early 90s, that local correlations can be threatened in a rigorous and exact manner if you have a computer. And this framework is called dynamical mean field theory. So what is it in a nutshell? So in the dynamical mean theory, the Green's function is written here, and the self-energy function is non-local in time, but it is local in space. So it's localized on sides of the lattice. This is a theoretical a theoretical school in Russia, so I must draw some diagrams. And in diagram language, this corresponds to a very particular diagram family. So you imagine the complete series of diagrams for the self-energy function. Just open Landau book without Landau, so the 9th volume. Think about all possible diagrams. They have U at the vertices and Green's functions as lines. In principle, you should take integral over time at each vertex, and also you should sum over all sides of your system or each vertex. So you don't do this. Instead of summing of our all sides, you just pick some particular side, but still you keep the entire diagram sequence. How can it be done in a practice? It's actually technically quite easy. You should consider what's called the Anderson impurity model. You take a single side and you hybridize it with some hybridization function, which is local, which is determined on this particular side, but it is in principle omega dependent, hence dynamical in the name of the method. This problem is relatively easy to solve on the computer. It can be solved on the laptop, and this gives you some self-energy function of the impurity model. So impurity model is much simpler than the lattice one, and you take this self-energy function and substitute it into the expression for the DMFT Green's function. That's it. The trick is that how do you choose the hybridization function? And this is the famous DMFT self-consistency condition. It's very physical. You take it in such a way that the impurity Green's function is equal to the local Green's function, local part of the Green's function of the lattice. That's it. The other things are purely technical. So what's this? I asked an artificial intelligence to draw me what is correlated atom in a bath. I expected a bath like, Archimedes came from, but it drew me this. That's okay. So maybe at this point there are some questions about DMFT. This is almost textbook things. But yeah, okay. Now everybody in the auditorium knows what the DMFT is. Good. So what DMFT does, it transfers the spectral weight over the energy. This is the density of states for the Hubbard lattice of 8 sides at U equal 5 at relatively high temperature. The inverse temperature equals 3 here. So what it does, the spectral weight goes from the central part of the spectrum to so-called Hubbard bands. These things are formed. So this central peak, this is it exists. The DMFT is exact in the limit of a large coordinate number or the large dimension. For 2D, this is an artifact, but anyhow, this peak becomes more and more narrow, and at certain moment it disappears, and the system becomes dielectric, and this is the physics Hubbard was talking about. So this is purely local way to make the system insulated. But this is actually, at least in 2D, very far from what happens in the real system, because the system exhibits, as I told you, very strong antiferromagnetism. And if you say measure, I will tell you how the antiferromagnetic susceptibility at this temperature, it's pretty high temperature, but equal 3. Then the DMFT predicts you that the system is basically at the edge of the phase transition. So how do you implement the ordering in the DMFT? You introduce this checkerboard. You see there are blue and red atoms, blue and red sites now. So they are equivalent, but you assume the symmetry break. You assume that the spin polarization is up for red ones and down for blue ones. Then you can introduce also an external antiferromagnetic polarizing field in your model and measure the susceptibility, the spin susceptibility to this external field, and the result is drawn in the right panel. So it always starts. This is Curie constant, so this is the susceptibility divided by beta. So what you see that the susceptibility indeed grows faster, and then just the phase transition occurs of the inverse temperature. Sorry, this is beta, and this is beta equal 3.1 on something like this. Phase transition of this. What's the problem? The problem is about the numerically exact data. They do not show, of course, any kind of the phase transition, because Berman and Wagner do not allow it to be ordered. And after all, this is a finite system. It's never shows a symmetry break. And you see, actually, this is very particular behavior. Up to certain temperature, DMFT is almost exact. So, well, there is an error bar in this point. So, of course, this is probably a coincidence, but qualitatively, the situation is like this. And then suddenly, DMFT becomes completely wrong, I would say. Because what we have here, we have antiferromagnetism, but we don't have ordering, we have antiferromagnetic fluctuations. So this is a region where basically Mott's view is more correct. There are strong antiferromagnetic fluctuations. How can we handle it? Well, first we can of course somehow try to improve diagrammatically the DMFT results. There is a couple of theories that are quite similar one to another, which aim to construct such a diagrammatic correction to DMFT. These are D gamma A and DF. I'm used to use TF dual fermions, but indeed there is no big difference between them. So I'm not going to explain the derivation of the dual fermions technique. I will just show you the result. So if you go from DMFT to DF, then operationally what you have, you should replace the impurity Green's function with somewhat different expression, which is non-local in space. And this is sigma df. This is so-called dual self-energy. There is diagrammatic series for this quantity. This is the leading diagram. In these diagrams, the vertices are vertex parts of the impurity model, and the lines are non-local parts of the Green function. Basically, doesn't matter. This is a correction. So you somehow improve the DMFT result. You bring some non-locality. You bring some short-ranged correlations, but you cannot, of course, qualitatively change the prediction of the DMFT, at least by taking into account Seinfeld diagrams. All of us know to change the picture of the phase transition, you should, in principle, sum up the infinite diagram series. So, well, you can of course use some diagram series like ladders or parquet, and this gives you something. But again, open Landau book and read that near the phase transition there is no leading diagram sequence. You should either sum up all the diagrams, or invent something more interesting. Good, and this is what we are going to do here. I'm sorry, this is a hard point. This is a single slide for which I would ask you to watch the expressions, to watch the derivations. I dropped most of formulas, but this I could not. So let us start from the partition function of my Hubbard lattice. So this is an action, and I'm going to calculate susceptibilities. So there is some external polarizing field M. So this is a standard expression, and I will put this say functional unity under the integral. So this is just 1. This is Gaussian integral. H is a 3-component vector, which is the same for all sides, but antiferromagnetically ordered. Yeah. So this is in fact effectively some field. And if you take an integral over H, you immediately see that this is 1. So put it here. What we are going to have, yeah, there is integral over the Grassmannians, and there is an integral over this new field. So I rewrite my partition function as this integral. So this is integral over this new field, and tilde z is written here. So what we have the initial action of the Hubbard model. From this term, you have H acting on the spin variables. Yeah, so the polarizing field which now fluctuates, and you have S squared term here. S is the total antiferromagnetic polarization of the system. So if you have it squared, you have counter antiferromagnetic term, which acts which is fully long-ranged, so it acts between any two sides of the system. So this is global polarization, square of it. So as J prime presents here. So this is rigorous. This is not very physical. This is math. But what you have now, you have a counter ordering term, and there is a quantity called lambda here. This is parameter. So this is a real number, real positive number, which I can tune. And I'm going to tune it in such a way that the antiferromagnetism, which arises here because of the Hubbard physics we have discussed before, so this antiferromagnetism is suppressed by this term. So there is basically ordering physics here, and this is counter-ordering. I'm going to compensate them. If you draw a couple of formulas, there is a simple formula which defines this parameter lambda. It appears to be somewhat like half of the Hubbard U numerically. Say U equal 5, then this optimized lambda star is 2 probably. Yeah, good. So we started from a single Hubbard model. We obtained a number of Hubbard models. You average it, but these Hubbard models are modified. They show less global fluctuations. But this is actually what we need. I call it the central problem of the method. This is what we need. So we need just to average the Green's function over this ensemble. This is, as I told you, the Hubbard model without long-range fluctuations. Probably this is what is good for the DMFT-like approximation, because DMFT takes into account the local physics, and we erased the global fluctuations out from this. Well, there is minor issue about the long-range interaction here. In principle, the DMFT is a theory which targets the local interaction, but it's easy to get rid of this problem. So just rewrite the expression like this, yeah, where S tilde is the H field dependent averaged polarization in the system, and then do beaming fieldish. So forget about the fluctuation term. I purposely wrote you that the system is large, that's 64 atoms, so the fluctuations are 1 to 64. Forget about them, they are small. After this, what we have usual normal Hubbard model at each h. The only difference is that this Hubbard model is subjected to a self-consistent external field. So this is IH minus lambda S tilde. So what you do DMFT, but you self-consistently find not only delta, not only the hybridization function, but also the field acting on the system. And you should do it for each value of h. Good. Don't look here. Don't look in details. Anyhow, this is an illustration. This is a real scheme. This is an illustration how the method is implemented. What is important? Important is that the field H is a 3-component vector. But if you tend your external polarizing field to zero, then the system is rotational invariant, and there is no problem to integrate over the angles. You do it with a single line on a piece of paper. So all you need to take an integral over the value of h. So this is one variable, single variable numerical integration. It's easy to do. Good. That's all about formulas. Relax. Let me show you the results. So this is the logarithm or the integrand of the formulas we're dealing with. So what we have this fluctuating field. We have this quantity z tilde h. Remember, yeah? This is, I take logarithm of this, and I plot it as a function of not the external field, the fluctuating field, but the average value of the spin polarization in a system. So what is drawn here is exactly the graph of Landau free energy, what is called Mexican hat in many theories. That's quite interesting graphs. So different colors are different temperatures. The more blue is a lower temperature. The left-hand panel is about the half-field system. So what do we have? First, we have like a parabola, and then at beta between 3 and 4, suddenly the curve becomes Mexican head shaped. So there is a minimum here. The position of this minimum is a solution of the DMFT. So DMFT is like neglection of fluctuations in the theory. But you see that, for instance, for beta equal 4, this minimum is very broad. And of course, there are fluctuations. There are strong fluctuations. You cannot actually neglect them. And this tells us why DMFT was wrong for this temperature. So the fluctuations of the parameters are extremely high. Well, for lower temperature, the minimum is more pronounced. And of course, here the value of h is almost constrained, or value of the spin polarization is almost constrained. Still, this is a Mexican head, so there are fluctuations of the direction of this h vector. Yeah, this is a rotation figure. But at least the value of h is constraint of spin polarization. Well, what we have on the right, this is the same curves plotted for different value of the chemical potential. So this is not exactly half filling. This is like 10% doping. And you see that the picture is completely different. You do not have this Mexican head behavior. The system is in the fluctuating regime even for low temperature. And this tells you actually why doped Hubbard model is so hard to solve, so hard to analyze. It's always in a fluctuating regime. It's somewhat near the quantum phase transition point, so to say. Yeah. So what's the difference between the solid and dashed curves? This is the DMFT, and this is the dual fermion correction taken into account. So you see the difference is not big, and that's a good sign. This means that we are working with a controllable expansion. Good. So this is the k-dependent self-energy function for the lowest Matsubara frequency. So the dots, the crosses are a numerical data obtained by the QMC simulation, and the curves are our data. Well, of course, each series of dots costs basically a day of supercomputer time, and the curve is obtained in a minute. So you can guess about the how good or how bad the method is, but it is, at least it's not very bad, at least. Yeah. Well, these are very interesting plots. This is the same self-energy at the lowest Matsubara, but for the 6% doped system, beta equal 5. Why these curves are interesting? Because this set of values became a benchmark, basically, for the numerically exact methods. There was a science paper by Antoine George's group, probably last year. They work on some set of numerically exact methods, and they came out with this set of points. So here the blue dots are our QMC results, and these two sets are obtained in that science paper. So what you see from here is that the error bar of these numerically exact methods is actually huge. If you look with an eye, then probably we are even in the corridor of error bar. Good. This is a spectral function. Well, if self-energy is good, then spectral function is also good. Compared to the QXC, it's almost the same. Well, this is very interesting. This is Curie constant, so susceptibility, antiferromagnetic susceptibility times temperature. What we see here, for low temperature, as I told you, you have seen this graph, yeah, with QMC with DMFT wrongly predicting a phase transition. So now this is the FLF method. Again, two curves, with and without the dual fermion correction, and again the curves are quite close one to another. It starts from 0.5, then it grows, and then it goes to some constant value. Why? Actually, it's very simple. It's not widely known, but it's very simple. What is Curie constant? Why do I call this graph a Curie constant? Yeah, because this quantity is a constant if you have a well-defined degree of freedom. If you have some magnet, you allow it to fluctuate and calculate susceptibility, then Curie constant determines the magnetic moment value, basically. Yes. So what it says here, it says that a big collective spin is made of these 64 sites, and they fluctuate as a whole, as a single big magnetic arrow. What's the value of this arrow? This is 64 times the spin polarization of single side. Good. So the same plot we have for the doped system. You see the tendency is similar, but you don't have this constant behavior yet, because the total magnetic moment is not forward yet. Probably would not be forward for lower temperature. There is a problem about the numerically exact data. These are quite low temperature, and even at half filling, the QMC data are very noisy, but qualitatively this is okay. So these are basically 2 QMC runs. So you can guess about the error bar of the QMC data. Okay. This is my last slide. This is the thing to think about. There are three formulas for the green functions. This is DMFT, this is dual fermion, and this is fluctuation local field. You see the formulas are of the same nature actually. We start from the DMFT. We take the dual fermion correction. The difference is, as I told you, there is a non-local correction to the Green's function. So the Green's function goes non-local, and in this fluctuational local field approach, the Green's function, it goes stochastic. It is not a number anymore, but a random value to be averaged over. I think that Francis Bott would love this approach, because, let me recall, he started with a picture of fluctuations. Okay, thank you very much for your attention.
Thank you very much for this nice, interesting talk. I suppose there will be many questions. At least.
Unfortunately, I'm unable to formulate the question in English exactly, so I turn to my mother tongue. Скажите, пожалуйста, правильно ли я понимаю, что даже и в ФТМФТ система остается антиферромагнитная, корреляционная длина бесконечная, спин-спиновый коррелятор на бесконечности не ноль и меняется по манхэттенской длине, а вот локальные корреляции, да, то есть виртуальные прыжки на примитивном языке на соседний узел обратно, теперь знают про то, кто там рядом прыгает, и локальные корреляции становятся жестче. Правильно это я?
Значит,
Вот
ответ
если
такой.
без
Чтобы не отвечать на ваш вопрос, я специально взял небольшую конечную систему 8 на 8. Да, то есть я предполагаю, что корреляционная длина...
Но идейно это вот как-то так все равно.
Да, значит, если бы мне пришлось рассчитывать решетку,
Да.
мне бы пришлось вот это флуктуирующее поле взять не трехмерным вектором, а векторным полем каким-то, да, как у Ландау-Гинзбурга.
Да.
Да, и тогда у меня все бы получилось для решетки, но у меня вместо однократного сеточного интеграла было бы, так сказать, что-то тяжелое.
Ну, я понял. То есть вы ушли от ответа. Понял. Спасибо, понял. Благодарю.
Но, Андрей, все-таки нет. Значит, давайте, вот что важно, да? Важно, что тут учитываются корреляции не short range, а, не знаю, как сказать, middle range, да, на расстояниях от порядка в данном случае 8. Мезоскопические, хорошо. И меня спасает то, что система все-таки двумерная. Да, 8 на 8 это уже много, 64.
Other questions? Well, if this is not the case, I do have a couple of one technical question and one probably philosophical question. The technical question is about, yes, to continue this discussion. In principle, as far as I understood, you can increase the size of your system somehow. You can easily to consider not 8 by 8 system, but some 16 by 16. But in your case, you just try to compare to some quantum Monte Carlo results, which you can do up to 8x8 cluster.
There are two reasons for choosing 8x8. First, indeed, I want to have a numerical reference. Second, I could take 16x16, but in the limit of the infinite system, how do I go back here? No way. No way. So, well, this curve, it scales proportional to the size of system, to the number of sites. Yeah. For large system, I would not have any fluctuations basically. And this would be a mistake because fluctuations persist. Yeah. Why? Because I took just a single field. I picked just a single channel of fluctuations, or pi for antiferromagnetic model. For large system, I must take a number of some fluctuational channels around this pi vector. And this, at least technically makes the things more difficult.
It becomes more difficult.
Yeah.
And the philosophical questions, in principle, when we consider lattice models, somehow we integrate out all some lattice degrees of freedom. I mean, I'm talking now about real materials. It introduced some kind of energy cutoff. We forget about electron lattice coupling, which is sometimes quite important. I wanted to refer to the talk by Sergei Ovchinnikov, yesterday talk. Sometimes, yes, we focus only on the electronic degrees, spin degrees of freedom, and forget about the lattice degrees of freedom, and try to find out some kind of very tiny energy effects, some kind of some complicated physics. But in reality, there will be some kind of energy cutoff, for example, some Polaronic effect, whatever, which kills all these some fluctuations, and the system will become more some kind of classical, less quantum. And this is some kind of question to me, in the sense that sometimes much simpler techniques like density functions, so static mean field plus Hubbard U, with some tuned interaction, work somehow more or less reasonably for many systems. In the case of strong fluctuations, of course, there is no way. It's only some dynamical mean fields here, and probably this diagrammatic extension to it, this non-local correlation fix. Is there any understanding, some kind of in such? I mean, how to go back to real materials? I mean, from models. I mean, it looks like some kind of a path which kills fluctuations, which cuts out all. There is no need to sum up all diagrams somehow, although you have some energy cutoff.
Let me be also philosophical. First of all, the energy scale hierarchy is very important for me because I do exist because of this. If you consider some standard model from high energy, there is no energy scale of less than 1 electron volt, but this is what makes us alive. Yeah, and this is all because of the scale hierarchy, because there are collective degrees of freedom. And this is also an example of the scale hierarchy. For the Hubbard model, you start with the T and U, which is about electron volts, and you go down at least orders of magnitude to have this antiferromagnetism, to have superconductivity, whatever. Now, of course, no one tries to describe human psychology in terms of the standard model. They always do some approximation. They always do some effective model. the question is, how do you do it? Which physics do you put in this? In certain sense, this is what you told about. This is an effective low energy model, but this is a reasonable way to derive this low energy model in a mathematically, well, not rigorous, but at least consistent way. The same is about your question. Well, if you forget about the high energy degrees of freedom, but if you do it in a consistent, in a verifiable way, then it's okay. You are on the safe side. But of course, you should think what you are doing. Okay. Sorry to be philosophical.
Well, this is a very philosophy. Yes. So yesterday we had a nice discussion with Sergey about that there are many mechanisms to kill this quasi-particle, this coherent quasi-particle peak, which appeared in dynamic fields here, like Polaronic effects, whatever. Disorder also tends to kill this quasi-particle peak. That many effects beyond the model.